Okay, next presenter is Issam Najam. He is the founder and president of Water Quality and Treatment Solutions, and there's a lot of stuff here about how great he is that he's asked me not to read. But I will point out that he did just win the award for Best Source Feature, if I'm not mistaken. Is that, yeah, on algal toxins. So he has a wide breadth of experience here, and he's going to be talking about Chrome 6 treatment removal. Thank you very much, Sam.
Thank you. Thank you, everybody. And I'll start my timer here. Thank you. So when Eugene had this brilliant idea of this session, we tried all to figure out what is it exactly we're going to say about each topic. So everybody picked different things, and hopefully what I picked is what he had in mind for this session. We'll find out. So I was tasked with talking about hexavale and chromium, and I am not approaching it from a specific project, but I thought in the interest of getting this information out to small systems who have never necessarily experienced treatment, to sort of dive into, frankly, to dissect the treatment question of Chrome 6. How is it that we treat for it, and why does that treatment work and that treatment does not work, or things like that. So we'll go through this exercise, and hopefully it'll be informative to you as well. So I do want to acknowledge the fact that much of the information that I'm basing my discussion on is from Water Research Foundation project, 4450 for reference. We conducted it in partnership with Hazen and Sawyer and Waterworks engineers a few years back, and it had support from 11 water systems that contributed funding to it, as well as water sources for testing. So with that, here's what I'm going to cover. I'm going to lay the ground on the chemistry of chromium and sort of segue that into why certain treatments work for that chemistry. And then I'm going to discuss, in generalities, the 3 treatment scenarios that are implemented, or actually 4 of them. And I'm going to take a shot at a 500 GPM well and discuss cost numbers. So chromium as a natural element exists in a number of oxidation states, as we call them, but the 3 most dominant ones are the elemental one, which is just a pure element itself, and it is part of the Earth's crust. But as it enters the environment, as it's exposed to oxygen, as it goes into water, it can exist in really one of 2 main states, either as Chrome 3 or Chrome 6. Chrome 3 is what's referred to as trivalent chromium, and Chrome 6 is the hexavalent chromium. So these are 2 different oxidation states of chromium, and they make an element that is vastly different from the other. So trivalent chromium, Chrome 3, is non-toxic. In the US, it's considered to be an essential nutrient, although there's some more recent debate about that. And I have to emphasize in the US because other countries disagree with it. It is insoluble in water. So when Chrome 3 is present in water, it precipitates in one of 2 forms, depending on concentration, depending on the chemistry of the water. It can precipitate as a crystalline structure, which is that Cr2O3, and that is a more hard, solid precipitate. But in typical water applications, it actually precipitates more as a chromium hydroxide, very much like ferric hydroxide and aluminum hydroxide precipitate. So it's a solid product, but it's a very amorphous and light product. So Chrome 3 is insoluble and it precipitates very readily. But if Chrome 3 is oxidized to Chrome 6, and we'll talk about that reaction in a little bit, now we have a whole different element, or I should say ion, that is toxic, that is highly soluble in water, But what is also important for the treatment purposes is to recognize that while as an ion it is positively charged, if it's in water, it binds with oxygen immediately and it generates a negatively charged ion. And that is the CrO4 that you see up there. So when we talk about Chrome 6, in water, it's pretty much all CrO4 So it's a negatively charged ion with a divalent negative charge. Under acidic conditions and high concentrations, Chrome 6 can also form dichromate. And if you did work in research labs a few decades ago, like I did, we used to clean glassware in dichromate and play with it all the time. So I'm still okay. But it's a strong oxidizer, so it's good at oxidizing organic material on glassware, as in cleaning glassware. But under typical conditions, that is not what we have in water. We have the CrO4 it's the divalent negatively charged ion in water. And there are many other oxidation states that are listed at the bottom, but really they don't exist under normal conditions for the purpose of what we do in water treatment. So how are these two oxidation states related? On the left, you see the trivalent chromium, the Chrome 3. On the right is the hexavalent chromium. So we go from trivalent chromium to hexavalent chromium through oxidation. That means exposure of that element to oxygen for extended periods of time, or for chlorine in short periods of time, it can oxidize it to Chrome 6. And long and term is all relative, right? I'm not talking about minutes, I'm talking hours to days. And you can also take hexavalent chromium back to Chrome 3 through chemical reduction. And so we look for reducing agents that we use in water treatment, and there are two that are commonly used for Chrome 6 reduction to Chrome 3. Ferrous iron is one reducing agent that we use to take Chrome 6 back to Chrome 3. And also stannous tin basically also is an agent that we can add to water and use it to reduce Chrome 6 to Chrome 3. And, you know, we see them expressed in different ways. So I have it up here. Chrome 3 is, you see it expressed as Cr3+, Cr Roman numeral 3, Cr3 the number. But in water, because it is highly insoluble, when you have Chrome 3, you pretty much have CrOH3 as a solid material that precipitates. And on the right is the hexavalent chromium. And you see it expressed as Cr6+ or Cr, Roman numeral 6. But in water, it is pretty much CrO4 2-. So we have two states of chromium. In its reduced form, it is a solid precipitate. In its oxidized form, it's a dissolved, negatively charged ions. Okay? So knowing that chemistry, now we can think about treatment. So on the left-hand side, you have option 1 for treatment. If you're trying to remove Chrome 6, you can think about removing that ion of that Chrome 6, and that's the CrO4 2-. So we have a negatively charged ion that we want to remove, and ion exchange is the default process for removing ions from water. And so to that extent, ion exchange resins climb up to the top of the list of options to remove Chrome 6 as in the way it is present as a negatively charged ion. Similar to nitrate, which is a negatively charged ion, we use anion-based resins to remove nitrate, and we use the same type of resin to remove Chrome 6. But we also can use what we refer to as weak-base anion resin, and I will talk about that a little later. But it is a resin that has a very high capacity for Chrome 6, but it requires that the pH of the water be reduced down to about 6 before the water goes into the ion exchange process. And it can last for 100,000 bed volumes and more, depending on different water chemistry characteristics. But the bottom line is you do not need to regenerate it with salt. You simply replace it, just like you do with GAC. You dispose of it, bring new resin, and put it back in service. But again, the problem is you got to depress the pH to pH 6, and then obviously bring it back up afterwards with a caustic to make it okay to put in the distribution system. On the right-hand side is the other option of saying, okay, if I want to get rid of Chrome 6, let me just turn it to Chrome 3. So we can use chemical reduction to take Chrome 6 to Chrome 3, and all of a sudden we've taken the toxicity aspect of the chromium and turned it into a non-toxic product. The question there is, okay, it is no longer Chrome 6, what do I do with it? So we have two options. You leave it in the water, because the MCL is really just about Chrome 6. It's not about Chrome 3. It's not about total chromium. There is a total chromium MCL of 50 in California, but this is for systems that are far below that as total chromium. Or you may decide, you know, I don't want to leave it in the water and put it in the distribution system. I actually want to remove it. And so now you have a solid product that is precipitate. You just got to make sure that you can coagulate it enough to make it filterable, and you just filter it out of the water. So that is really the paradigm of Chrome 6 treatment. You're either treating the ion, that is the Chrome 6, with ion exchange, or you're turning it into the solid precipitate of Chrome 3, and then deciding whether to remove it from the water or not remove it at all. And we're going to talk about these processes. So here's a schematic of what we refer to as the strong base anion exchange resin process, I should say. This is very much similar to what you use for nitrate treatment. And so we have raw water coming in. You may go through a strainer to remove suspended material to protect the resin. Then you go through a resin process, and coming out, you go into a treated water tank, and I'm not listing the chlorine here for disinfection, but that's a different issue. And you use a salt brine to regenerate the resin. You collect the waste brine, and you haul it off-site. You may be able to recover some of the water, specifically doing slow rinsing of the resin, and put that back into the head of the plant. And there are different variations on how you manage this to minimize the waste, but this is the crux of the process. Very much a typical ion exchange process, the way you use for nitrate. So what do you expect to see out of it? If you look at the Chrome 6 level as a function of time, you go through a runtime that might be days, depending on the quality of the water. If it's high sulfate, it may be hours. If it's lower sulfate, it might be a week to 2 weeks before you have to regenerate. And so you go through a regeneration. Every time you generate a waste, you go back to start of a run, and you go through, cycle through these runs. Obviously, everything you removed from the water is now concentrated in that brine, and that becomes really the tail that wags the dog. That becomes the challenge with whether this is a process that's going to work for a specific system, or it's got a fatal flaw because of the disposal requirements of that resin. And so the strengths about it is that it's a common industry experience. You need very little resin replacement, and I say minimal because you lose resin through backwashing and regeneration, so you have to replenish every year, replenish a small amount of that resin, depending on the loss rate. It is likely to require the smallest footprint compared to the other two processes, and it's likely to cost less than the other two processes as well, especially for a small system. It does generate the waste brine that has thousands of milligrams per liter of TDS, and I just picked a 30,000 number as a minimum. Disposal will likely be a fatal flaw for a number of applications. And higher sulfates would greatly increase the regeneration frequency and make it even more of a problem to be able to manage that salt disposal. The weak base anion exchange resin, as I mentioned, it's similar as a product, but not as a process. As a process, you're simply adding acid before the process to lower the pH, and it can be a mineral acid, also can be carbon dioxide, depending on specific situation. But you run it through the resin, and it lasts, as I mentioned, 100,000 plus bed volumes, and then you add the caustic afterwards to raise the pH back up and go into a treated water system. And the only reason we talk about backwash water here, mainly during installation, just like you heard before about GAC installation, you need to remove those fines. So in an operational sense, you get months to year plus of operation before you have to put in a new resin and dispose of that resin and start a new operation and move on from there. It lasts a long time, but it's also at least 3 times as expensive as the typical nitrate type resin that you buy. And so, and on top of that, if you do the math, it's actually almost 10 times as expensive as GAC. So if you think of GAC replacement and you think, okay, you have a good sense of how expensive or how inexpensive that is for a certain system, this is about 10 times that on a cubic foot basis. So it's a significant cost. The strength of it, there's no salt regeneration required, which is great, and does not, in other words, does not generate liquid salt, liquid waste, other than the initial installation backwashing. The problem is it requires a significant amount of acid, and out here out west, our groundwater is high alkalinity groundwater, so it takes a lot of acid to bring the pH back down to 6, and that means also it takes a lot to bring it back up with caustic on the other side of the vessels. It can accumulate uranium to significant amounts, and so even if the uranium may be non-detectable in the raw water, you accumulate enough on it on the resin that it might become a significant waste disposal issue. And there are systems that actually cut off the run early enough so that the uranium is not a radioactive waste, does not make the resin radioactive waste, and basically waste that capacity that is still available for Chrome-6, but they don't want to go that far on the uranium accumulation in the resin. And it is likely to be the most costly compared to the other options. The other process is what we refer to as reduction, coagulation, filtration. This is where now we are reducing the Chrome-6 to Chrome-3 and then coagulating it and filtering it out of the water. And this is the typical coagulation filtration process that you heard about this morning for arsenic treatment. It's exactly the same. You just add a reducing agent up front, whether it's ferrous iron or stannous tin. And you may have to add a polymer to make the material a little more filterable. You add chlorine, and you go through just a regular sand anthracite process to collect the material that you just filtered. Go to treated water and then pump it out in the system, and use treated water to backwash the filter whenever turbidity starts to show up on the effluent. It does generate a significant amount of backwash water, so it's always good to be able to recover some of that water through a settler and then dump the waste either off-site or to a sewer. And again, operationally, you're looking at hours of runtime, maybe more than a day, but a typical filter operation, you run water through it, you go through a backwash, and you process the backwash water, and you go back into just cycling through the operations of the filter. The good thing about it is that this backwash water is low enough obviously in salt or in chromium that you can, 5 minutes, you can discharge it to many sanitary sewers would accept it. In fact, it might be a little too dilute for some wastewater agencies that they need you to reduce the volume just because it's too dilute for their wastewater plants. There's no proprietary components to it. If you're using ferrous as a reducing agent. And it's a common conventional filtration process that many operations staff are familiar with. It does generate a significant amount of waste backwash water, 2 to 5% probably, and is likely to require the largest footprint compared to the other processes. And finally, the reduction-only treatment approach, which is the system that Coachella Valley with Corona Environmental pilot tested at full scale. down in their system. And basically, it takes the raw water out of the well, adds stannous chloride to reduce the chrome 6 to chrome 3, and just may or may not need a contactor just for the contact time, and then just put it out in the system and let the chrome 3 go into the distribution system as chrome 3. It is not chrome 6 anymore in that sense. So you can see how simple it is, and it can be attractive from that perspective. It's obviously the simplest approach, lowest cost, no waste generated, because you're just adding a chemical. It's almost like the concept of using sequestering agent for manganese treatment in wells, and just not letting it precipitate out in the system, and just put it through. It's in its infancy as a concept. There's no control about the fate of that chromium in the system. A significant amount of it may precipitate in the distribution system. So I have questions about, well, during flushing, am I going to exceed a discharge limit on chromium if I'm flushing a pipe that's accumulated years of chrome 3 in it? Will the chrome 6 levels increase dramatically if you go through a main disinfection? And even though you flush it afterwards, that disinfection may redissolve a significant amount of chrome 3. I don't know. And as I understand it, right now it's still a single chemical supplier for the stannous chloride, and I know there's a patent on its use that's going to expire in 2020, but I don't know what the future of that patent will be, and that's a little throws a wrench into this issue. So I'll do it quick. An example well, 500 GPM well, took a shot at 15 microgram per liter chrome 6, utilization rate of 75%. That means generates about 600 acre-foot per year. A low sulfate of 25 milligrams per liter, and the alkalinity of 150, and just went through some cost development that I want to throw out in front of you. Hope you can see this. This is a graph on the left is the capital cost as a range, because there's no design, so this is always a range. An SBA for the regenerable resin, WBA, and the RCF. And as I mentioned, you can see the RCF capital cost is significantly higher because it's got a lot more components to it. On the right is the annual O&M cost, and the WBA, because of the resin replacement and the waste discharge, is the higher number. And so if we go to the total annual cost, if you amortize the capital and add to it the annual O&M cost, is on the left, and now things shift around. So because of the low annual O&M cost of the RCF, it comes down below the WBA as an average range. And on the right-hand side is the total water cost. And if you take that annualized cost and divide it by the 600 acre-feet, that's how many dollars per acre-foot you can expect for that. The cost of building and operating each of these technologies, and this puts it in perspective to what you pay for typical water. So with that, these are the take-home messages. We can remove chrome 6 either at the ion itself or reduce it and then figure out whether to remove it or keep it. We can achieve that through chemical oxidation and reduction. Leaving the chrome 3 in the water is an interesting concept. It is cheap and simple, but there's a lot of questions around it. But if the removal is required, SBA ion exchange continues to be the lower cost process, but it really requires a water with low sulfate. You go up in sulfate concentrations, the regeneration frequency just becomes too high, and it may choke the brine disposal capacity of the system. And with that, I thank you for your attendance.
Very educational presentation. So we have questions.
Unfortunately, Conrad has a question.
It will be eventually posted on one of the sections domains. So either the section website, Vimeo, YouTube, they have channels. So.
And last question, the last treatment, the basic, simple, sounds great for treatment and simple for operations. Can you add a sequestrant just to keep it in suspension in the distribution?
Yes, you can add a sequestering agent, very much like manganese treatment, and try not to let it precipitate. I have an opinion about sequestering agents because we also use precipitation to protect pipe surfaces through the calcium carbonate precipitation. Sequestration also prevents that. So I'm not a big fan of sequestration for that reason.
Okay. Thank you.
I have a question on the Chrome 6 and reducing it to 3 and just letting it go into distribution. Have you come across any evidence that the 3 can go back to 6, or have they found that it does precipitate out? Because you mentioned it seems like that's the easy solution, but there's some questions. Is that because there is some data that shows that it changes forms?
Yes, it does. The trick, though, is that oxidation reaction is slow, so it takes several days to go back up in concentration. So, it depends on the residence time in the system. You may get some oxidation under most conditions, but it may not come close to the MCL, wherever that MCL ends up being, I have to say. But it does happen, it's just slow.
So the CR3 outside of the United States is questionable, right? You said within the United States it's accepted as like an essential element, but outside of the United States there's research that proves otherwise. So with the last method and leaving the CR3 in the water, is there like a potential that in the near future that's going to be an element that's going to be needed to be removed as well?
Well, it's a good question. My comment about outside the U.S. only in the sense that in the U.S., Chrome 3 is actually even in some medications that people use. So it's considered as a nutrient. In other countries, it is not used in that fashion. Whether eventually there could be a concern over Chrome 3 and the need to have an MCL for it, that's always a possibility, yes. And that would be an issue for that application.
So we have time for one or two more questions. I just wanted to remind everybody that after the next presentation from Kevin Berryhill, we will have a panel with all of the speakers from this morning being able to answer questions. So please do stick around if your question's not answered right now. So we have one more. Thanks,
Thank
Assam.
you.